Hello again. This is the second of 3 video tutorials developed by the Flood Hazard Research Centre at Middlesex University under the Flood-CBA 2 project. This tutorial concerns the theoretical underpinnings of project appraisal using cost-benefit analysis, so that we can hopefully understand the processes and the results more clearly. What we're doing here, of course, is comparing costs and benefits of different interventions in order to reduce flood risk. And in our experience, quantifying those benefits is quite problematic and sometimes full of uncertainty. But we have to identify those benefits in order to compare them with the costs, in order to isolate and develop efficient and effective flood risk reduction measures. In the previous tutorial, we saw this table describing how we compare the do nothing and the do something measures to assess their efficiency using cost-benefit analysis, converting the damages that we observe to annual averages and converting those to present values by discounting. What we are doing here is looking at flood damages that will occur in the future. And we should be very clear about this. Cost-benefit analysis is all about the future, not about the past. It's about decisions we might make now about future reductions in flood risk. And those flood risks involve assessing flood damages and flood damage data. And here this simple table differentiates between tangible and intangible flood damages, the tangible being measurable in money terms and the intangibles not. We also differentiate between direct and indirect flood damages. Direct flood damages being damage to a building and its contents. The indirect damages being the loss of industrial production in a factory affected by floods, either itself affected or the routes and communication links to the factory being disrupted by flooding. So all these flood damage and flood loss items are important, but not all of them can be included in cost-benefit analysis. Usually only the tangible ones can be included in this way. Now the diagram here illustrates the theory behind assessing annual average damages. And it involves 4 separate graphs, the first of which, in the bottom left-hand corner, looks for a fluvial environment between the discharge of a river and the probability of that discharge. So discharges which are very high have a low probability, and discharges that are quite low or small floods have a high probability. The diagram above that, diagram A, includes flood stage or flood level, which again increases as rivers increase in their discharge. Moving across to the top right-hand corner, we introduce flood damages, like included in the previous slide, which again increase approximately proportional to the depth of flooding on the floodplain. The heart of this system is when we bring all this data together in the coloured graph on the bottom right-hand side of the diagram, which we call the loss probability relationship or the damage probability relationship. And those who understand the maths of this will recognise that the area under this curve, in fact, is the annual average damage at that particular site. And what we've differentiated here between the orange area, which can be mitigated by a number of interventions that we could plan, and the yellow area, which is left as residual annual damages, those losses from flooding that you can't prevent, perhaps because the flooding is even more severe than you anticipate and defences get overtopped. This diagram is important to understand, and you may need to look at it several times. Now, coming to an example, we have a community here in the photograph where there has been a flood in the year 2000 in the UK. And the question we're posing here is to what standard of protection should this community be defended? What is the most efficient use of resources? And in this example, which is partly hypothetical, we have listed 5 different interventions, A to E, and they have different design standards in terms of the return period in years of the largest flood that is protected against. So, for example, Scheme E has a very high design standard protecting against very extreme events, very extreme flood events, whereas Scheme A has a very low design standard protecting against only the floods that occur once every 12 years. What we have for these particular schemes is an analysis here of the benefits accruing to that scheme as a result of its intervention and the costs. They're given here in millions of pounds, but they could equally be millions of euros or even millions of dollars. And you can see that Scheme A is much more expensive at 4.9 million pounds compared with Scheme A, which costs only £1 million. So there is, if you like, a ladder of increasing costs with the increasing standard of protection. Now, this diagram here is quite a nice little summary of that situation. What we are graphing is the costs of different interventions along the horizontal axis against the benefits accruing as a result of those interventions on the vertical axis. And we list here, or graph here, those 4 interventions, A, B, C, D, and E, E being the top one, which I've described. And anything to the left hand side of the graph is a good thing because the benefits exceed the costs. And anything below the diagonal line, which describes the benefit-cost ratio of 1.0, is not a good project because the costs exceed the benefits. So that diagram is quite useful in summarizing the benefits versus costs of a range of different interventions. If you look in more detail at the diagrams here, we can see that Scheme B has a benefit-cost ratio of 1.55, which is quite good. And that's the highest benefit-cost ratio from these range of interventions A to E. But intervention C has a higher value of benefit minus costs, or net present value, and that is the metric that we should be using because it represents the return on our investment. We put in a certain amount of money, in the case of C it's £2 million, and we get 3 million back. That's the highest level of intervention. And the graph on the left shows C, now the highest one of those 5 interventions. Another way of looking at it is to look at the incremental benefit-cost ratio. And that is the ratio between B and A. If we decide that we're not happy with A, Scheme A, we can proceed to Scheme B. And that proceeding to Scheme B involves more benefits than costs, and indeed the incremental benefit-cost ratio is 2.0. In the same way, if we're not content with Scheme B, we can proceed to Scheme C, and the benefit-cost ratio is still positive at 1.25. We see a return on the investment, the extra investment of going to C rather than B, of that figure represented by 1.25. However, if we're not content with C and we think we might advance to D, then the benefit cost ratio slips below 1.0, which means that the costs are progressing from C to D. Those costs exceed the benefits. And it's even worse if we go from D to E, where the benefit cost ratio, the incremental benefit cost ratio, is only 0.3. So the incremental benefit cost ratio gives you a measure of how satisfactory it is to move to higher design standards, higher levels of safety, higher levels of protection. But of course that comes with a cost, and we need to make sure the costs of higher standards of protection don't exceed the benefits that we obtain from that investment, that extra investment. The benefit cost ratio is all right by itself, but the incremental benefit cost ratio introduces a more complex and a more important dimension. And here we see that scheme C is best again, advancing from B with a benefit cost ratio at the margin, or the incremental benefit cost ratio, of 1.25. And after that, it's not good news at all. So another way of expressing the same thing is the graph we've got here, which again shows scheme C at a maximum, this time benefit minus cost. That's a good scheme. That's the one we should implement, other things be equal, and we certainly shouldn't implement scheme E, because that gives us a negative or below 1.0 benefit cost ratio and a negative result. However, there are complications in this process, and this is an interesting diagram produced by one of our colleagues at Middlesex University. On the left-hand side, we have things which we've called dead ducks, where the benefit cost ratio is below even 0.3. You're getting a terrible return for your investment. On the other hand, if you get a benefit cost ratio of 3.0, you can be pretty confident that this is a good scheme. It's certainly viable. If we move to higher benefit cost ratios, then we have to think carefully about whether we've made some mistakes or some other thing is affecting that result, because that result, generally speaking, is very high. Now, we have to acknowledge, as does everybody else, that cost-benefit analysis for flood risk management has merits and problems. Some of the merits are listed here. It's a transparent process. You can interrogate it, and it does lead to suggested expenditure amounts, which multi-criteria does not. On the other hand, there are problems. The cost-benefit analysis may not include those aspects which are most important, those so-called intangibles, and we have to be very conscious of that, be very wary of that particular problem. So, just to summarize, the Flood-CBA 2 system is rooted in an assessment of annual average flood damage avoided in the future, and its cost-benefit analysis aims to maximize outputs compared to inputs, maximizing the efficiency of investment to reduce flood risk, giving the best value for money. Thank you very much.